Hey, this is going to be a vodcast on Le Chatelier's principle. So, Le Chatelier's principle has to do with equilibriums, and the problem is with some reactions, they are equilibrium expressions. So, if we were in the business of making ammonia and we put together nitrogen gas and hydrogen gas, of course, we want to have 100% yield of this stuff. But the problem with making ammonia is after the ammonia gets created, it also makes nitrogen and hydrogen gas again. And that's what we don't want. So we really want this reaction to really shift to the right as much as possible when it comes to an equilibrium expression. So in 1888, French chemist Henri Louis Le Chatelier discovered a way to make some changes so that way you get a higher yield of your products by changing these different conditions. And in his principle, it states if a change is imposed on a system at equilibrium, the position of the equilibrium will shift in a direction that tends to reduce that change. So for the sake of Le Chatelier's principle, we'll be looking at three different things. We're going to be looking at the changes in concentration, the changes in pressure and volume, and the changes in temperature. Okay, so one of the first ones we're going to tackle is changes in concentration. And changes in concentration is happening when temperature and pressure are constant or temperature and volume are constant. So there's some important things to know here that when you add reactants, it will shift the equilibrium to the right. So in this case, if I add N2, it'll force my equilibrium to shift to the right and I can make more products. So when I say adding N2, I'm physically adding more nitrogen gas to the system. Remember, this is basically in a big, humongous sealed container, and I'm physically adding more N2 to the system with another tank or something. If I'm adding products, it will shift the equilibrium to the left. So if I'm adding more NH3 to the system, the equilibrium will shift to the, whoops, wrong arrow, to the left, which actually for making ammonia is not what we don't want. So just to kind of tackle some scenarios here, if let's see, I'm adding H2 to the system. So this is what I'm affecting. As a result, to compensate, the equilibrium will shift to the right. Since the equilibrium is now moving to the right to compensate, that means I am making more NH3, but in my N2 gas that's already in the system will decrease. Because since my equilibrium is shifting to the right, I'm making more NH3, but then my N2 is decreasing to compensate. To play a different scenario, if I decided to take out H2 out of the system, so H2, I'm physically taking H2 out of the system by some means, then to compensate for the equilibrium will shift to the left. Oops. There, arrow going to the left. Since my equilibrium will now shift to the left to compensate, that means I am making more N2, but then my NH3 is now decreasing. And you'll always look at the equilibrium arrow. The equilibrium arrow, whatever direction it's going to, those will increase, where on the opposite end they will decrease. The only one thing that doesn't take into consideration is what you are messing around with. So the blue arrows are the ones I'm messing around with, and the green ones are the ones where it's because of that it's being affected by my changes. So this is how changes in concentrations work when you're dealing with equilibrium shifts. Okay, for changes in pressure and volume, remember that pressure and volume are related. So, and there are three ways to change the pressure of a reaction system. We can either add or remove a gaseous reactant or product, add an inert gas, and basically one that's not involved in the reaction, or change the volume in the container. So, for the first one we're going to discuss is adding a gaseous reactant or product. And it's really the same thing as concentrations. It's really not any different. So, for example, if I'm adding NH3 to the system, since I'm adding NH3, my equilibrium will shift to the left to compensate. and since it's now shifting to the left, that means my N2 will increase and my H2 will increase to compensate. It will start to increase until it reaches equilibrium again. So changes in pressure because you're adding or subtracting gaseous products or reactants is the same as concentrations. Okay, the next one is adding an inert gas. If you add an inert gas, let's say helium is a good example, or maybe neon, they will have no effect on the concentration or partial pressures of the reactants. So there is no shift in equilibrium when you add some gas that's not going to react with any of the reactants or products. So that's pretty easy to think about. Okay, the last of the pressure changes is when you change the volume of a container. So when you're changing the volume of a container, pressure and volume are related. So here's my container, here's my piston. So I'm going to, for an example, let's say that my volume is decreasing. So I'm basically putting the piston head down. My pressure inside there will actually increase. Okay, so in my first example, you have to count how many molecules you have in your reaction. So for this example, I have a total of 4 molecules. So 1 plus 3 is 4. On this side, I have 2. In the second example, I have 1 plus 1 is 2. And then I have 2 here, so 2 and 2. Okay, so if I am lowering my volume, I'm basically adding more pressure. I'm basically squeezing this reaction to the right. It's going from 4 molecules to 2 molecules because I'm lowering volume and increasing pressure. I'm kind of squeezing them in together. The equilibrium will shift to the right to compensate. So in this example, my equilibrium will shift to the right because it's going from 4 molecules to 2 molecules. I'm kind of squeezing these, I'm forcing these together to go to the right. Because this is an uneven number of molecules on both sides. On the bottom example here, since I have equal number of molecules on both sides, it will not change at all. No volume or pressure changes will shift this equilibrium because the number of molecules are the same on both sides. If I take the opposite, oops. If I take the opposite of this and say I'm going to erase this. I'm increasing volume. So if I'm increasing volume, I'm lowering my pressure. And since I'm increasing volume, I'm giving them more space to move around, then the reaction equilibrium will shift to the one that has more molecules. It'll start to shift to the left. So since it's shifting to the left, that means my N2 will increase and my H2 will increase and my NH3 will decrease because I'm giving them more space to move around. The equilibrium will shift to the left. So pressure and volume are related, and it does matter how many molecules you have. And if it has equal number of molecules, it has no change whatsoever. Okay, the last one we're going to tackle is changes in temperature. So for the previous changes that we had, the equilibrium constant K did not change in any of them. K remained constant throughout the whole process. And that's a very important point to know when we're messing around with temperature. When we do mess around with temperature, the K does change. So remember that. K changes when you mess around with temperature. It goes with equilibriums. It also goes with reaction rates. So for changes in temperature, it does affect the way it shifts. And the direction of the shift depends on whether it is exothermic, where the reaction is giving off heat, or endothermic, where the reaction is absorbing heat. Okay, so when a reaction is exothermic, what I'm going to do is the reaction is basically giving off heat. And to kind of help me understand this, since reaction is giving off heat, I'm going to write the word heat right here. So I know that this is an exothermic reaction, and I'm going to treat this heat like a concentration. And the same rules apply for stuff in concentrations, except that this is heat. So for example, and here it says think of heat as a product. Raising the temperature push towards reactants, therefore equilibrium shifts to the left. So if I increase the temperature, I have this in a big vessel and I increase the temperature, so this is what I'm messing around with. Then my, just like concentrations, my equilibrium will shift to the left to compensate. And what's going to happen is my N2 concentration will increase, my H2 concentration will increase, and my NH3 concentration will decrease because my equilibrium is shifting to the left. So once you figure out where to put the word heat, because it's exothermic, it's the same as we did for concentrations. The opposite is true if we are lowering the temperature of the system. So if we're lowering the temperature of the system, then my equilibrium will shift to the right to compensate. Then since it's shifting to the right, my NH3 will increase, my H2 will decrease, and my N2 will also decrease because my equilibrium is shifting to the right. So whenever there's an exothermic reaction, consider putting heat on the right and make it like a concentration. The opposite can be held for when it's endothermic. So when it's endothermic, I'm going to write the word heat actually on the left side, because now the reaction is now absorbing heat from the system. Let's put this in a box. If I raise the temperature of the system in an endothermic reaction, my equilibrium will shift to the right to compensate. And it's because it's shifting to the right, my NH3 will increase, my H2 will decrease, and my N2 will decrease to compensate. So it's important to remember, exothermic reactions, we write the word heat on the right side. Endothermic, we write the word heat on the left side, and we treat them like concentrations. And K does change when you start messing around with temperature. Okay, for the Haber-Bosch process, what can you do to make as much ammonia as you can? So obviously one thing you can do is you can increase your concentrations of N2 and H2, because remember the idea is we want to make as much ammonia as we can. We want the equilibrium to shift to the right as far as we can. So step one is to increase my concentration of N2 and H2. It will definitely increase the equilibrium to the right. Since I have 4 molecules on the left and only 2 on the right, whoops, what I can do is put this in under very low volumes. Whoops, I'll forget my piston. So I can lower my volume to increase my pressure. So very high pressure. It'll also shift it to the right. It's the second thing I can do. So first thing was concentration, second thing was that. The third thing you can do is, since it produces heat, it's an exothermic reaction, you can run this at a very, very low temperatures. You can lower your heat, make this very cold, and it'll shift it to the right. Well, when they make ammonia, they do all three processes at the same time. It is not just one. So to make commercially ammonia 100%, close to 100%, they do all three at the same time. All right, so I hope this helps you out.